When talking about the relationship between the whole and its parts, there are three properties that are often mistaken for one another. In classical mechanics, this is not really a problem because most of the time you have all three. In quantum mechanics, these are distinct, and it is important to get them straight or you're going to get seriously confused. We're going to talk about what it means for a system to be divisible, reducible, or decomposable. Let's start with the first two, divisible and reducible. We say a system is divisible if we have a process that divides it into two independent parts. That is, we start with the state of a system and we end up with two states of two independent systems. The two systems are independent in the sense that we can manipulate one without affecting the other. Note that the description is at two different times. Mathematically, we have an evolution operator PT that takes the state of a system S and returns a pair of states for the system S1 and S2. On the other hand, a system is reducible if the state of the whole can be expressed as the state of the parts. The system is made of two or more parts, and describing the parts is the same as describing the whole. Note that the description is at the same time. Mathematically, the state S is equal to a pair of states, one for system S1 and one for system S2. Now this may seem like splitting hairs, but it's important, so let's look at a couple of examples. Consider a planarian worm. You start with a single worm, you cut it up into three pieces, you wait a little bit, and you end up with three worms. The planarian worm is able to regrow not only its limbs, but the head, the eyes, everything. Therefore, the planarian worm is divisible into three worms. However, the planarian worm is not reducible to three worms. If I'm describing one worm, I'm not describing three worms. One worm is not secretly made of three worms. So a planarian worm is divisible into three worms, but not reducible to three worms. On the other hand, consider a magnet. If you want to describe the state of a magnet, we can describe it through its north and the south poles. We can in fact think of the magnet as made of two parts, at least to a first approximation, where the magnetic charge is concentrated. Therefore, the magnet is reducible to the north and south poles. However, we cannot divide the magnets into a north and a south pole. If we try to do so, we do not end up with a north pole separated from a south pole, we end up with two magnets. So the magnet is reducible to north and south poles, but not divisible into them. So these were macroscopic examples. Now let's give two microscopic examples. Consider a muon. If you wait long enough, a muon will decay in an electron, a neutrino, and an antineutrino. We start with one particle and we end up with three particles. We are not doing the chopping this time, it just breaks apart by itself, yet at the end there is no muon, but three remnants. So we can say that a muon is divisible into three particles. However, the muon is not reducible to the three particles. Given the state of a muon is not the same as giving the state of an electron, a neutrino, and an antineutrino. A muon is a fundamental particle, much like the electron and the neutrino. It is not secretly made of other particles. So the muon is divisible, but not reducible. Now consider a proton. We know the proton is made of quarks, and the gluons that bind them together. So a proton is reducible to its quarks and gluons. However, we cannot divide the proton into separate quarks. If we try to divide a proton, we put in so much energy that we end up producing a quark-antiquark pair. So if you try to divide a proton, you get two aggregates of quarks and gluon, not an isolated quark or gluon. Therefore, the proton is reducible to quarks, but it's not divisible into quarks. Now, why is this important? Because the characteristic feature of a quantum system is not indivisibility. Saying that an electron is indivisible can be misleading. In some detectors, an incoming electron is effectively broken into a shower of many electron, positron, and photons. One particle comes in, many particles come out. In that sense, the electron is divisible. The energy present in the quantum system can always be, at least in principle, rearranged into other quantum objects of smaller energy. But quantum systems are not reducible. That is, the description of a quantum system cannot be indefinitely refined into subsystems and subsystems and subsystems. That is the issue. That's what makes it quantum. We have a limit beyond which we cannot go. Even if there were parts doing something, that dynamic, that information is not accessible to us. It is beyond what can be described. Quantum systems, in fact, can absorb, radiate, decay, entangle, and all these are forms of merging and splitting. A fundamental particle, therefore, is not an indivisible, immutable object. It is an object that, as far as we can tell, has no discernible substructure. We cannot describe the object in terms of another. So that is why it is important to be precise and understand the difference between divisible and reducible, because if we don't understand exactly what makes a system a quantum system. Irreducibility is what a quantum system is all about. Now let's look at the last property, decomposability. We say a system is decomposable if we can calculate one or more properties by combining independent contribution from separate components. The components are not necessarily parts of the system itself. For example, an infinitesimal displacement can be decomposed into the sum of the horizontal and vertical part, but there is no sense in which the horizontal line is part of the diagonal. Mathematically, we have an addition operation that taken two states gives us a different state. And then we have a property for which the property of the sum is equal to the sum of the property. So let's give an example. Consider an infinitesimal displacement. Work is a linear functional. We apply the force to a displacement and gives us the work along that displacement. And this is the same as applying the force to the horizontal and vertical components and summing. Therefore, work along an infinitesimal displacement is decomposable into the vertical and horizontal contributions. However, and this is the important bit, this is not true for everything. Not all properties work in the same way. Consider the length. Length is not a linear functional. The length of the diagonal is not the sum of the horizontal and vertical components. It is the square root of the sum of the squares of the sides. So length is not a linear functional, so the length along an infinitesimal displacement is not decomposable into a vertical and horizontal contribution. The fact that not all properties combine in the same way means that one has to be careful to think about linearity as an intrinsic property of the system. It is not just a feature of the object or of the property, but it's a joint feature. The way that we can decompose the objects works well with how we decompose the contributions to that property. Mathematically, the addition on the state space is a different operation than the addition on the real number, so the two should not be confused. And the fact that something is decomposable does not mean that it is reducible or divisible. If we cut the diagonal into two, we get two smaller diagonals, so a diagonal segment is not secretly made of an horizontal and vertical one. So the infinitesimal displacement is decomposable, but is not reducible or divisible into the components. So how does this relate to quantum mechanics? Now, in quantum mechanics, superpositions are decompositions. Like the infinitesimal displacements, when we are creating a superposition, we are not assembling parts. We are decomposing the problem into different contributions from different components. And this can be done in some cases. For example, we have linearity over time evolution. The time evolution of the sum is equal to the sum of the time evolution. The linearity between initial states becomes the linearity on the final states. We also have a linearity of expectation over the sum of the observables, so that the average of the sum becomes the sum of the averages. However, not everything combines linearly. If you get a superposition of states, this does not correspond to the linear combination of the respective expectations. Like the length of the displacement, not everything is linear, and this lack of linearity is precisely what does not allow you to think of a superposition as combining things into a probability distribution. In fact, in classical mechanics, the expectation is linear. The expectation of a linear combination is the linear combination of the expectation. And this is true for all property. This means that studying the component is the same as studying the whole. That is, the system is reducible to the components. And this linearity is what makes decomposability equivalent to reducibility in classical mechanics. That is why we don't highlight the difference in classical mechanics, because there is no difference at all. We can sort of do something like that with eigenstates of an operator. In that case, the expectation of the sum is the sum of the expectation, and we recover, in a sense, classical probability. But this is a special case. We need to match the components with the operator. And we can only do it for one operator at a time. And the reason we can't do it for all is obvious. The whole point is that quantum systems are irreducible. If we were able to recover this linearity like we have in classical mechanics, then the components would be parts. But the components can't be parts because the whole point of quantum systems is that they are irreducible. Therefore, superposition do not combine parts. They are not probability distributions. So next time that someone says quantum mechanics is a linear theory, think about this. The probability in general does not combine linearly in quantum mechanics, and that's the whole point. So you have the interference. Classical mechanics is a lot more linear than quantum mechanics. To sum up, one of the main difficulties in quantum mechanics is that we have to distinguish between these three concepts. These are different in classical mechanics as well, like we saw for the magnets, but in a vast majority of cases in classical mechanics, these concepts are interchangeable. In quantum mechanics, they're not. Divisible means we can break something apart into pieces. You start with an object and you end up with two. Reducible means that we can think of an object as being made of parts. Decomposables means we can think of a property of a system as being the sum of different contributions. Quantum systems are irreducible. We can't think of them as having parts. They are divisible because particle decay, quantum system can emit energy and so on. And they are decomposable. We can write superpositions, yet superpositions are not parts. We cannot divide the system into a component of a superposition. So if you can keep these three concepts straight in your head, I think it will go a long way to avoid quantum confusion.